All right, ladies and gents, let's talk distance formula / Pythagorean theorem. Another 12.5% chunk of your test. So remember, distance formula, Pythagorean theorem, it doesn't really matter which one you use, although it is situational. And so if you have a graph or you have a picture where you can definitely tell you have a right triangle and you can see it, I would suggest Pythagorean theorem might be the best way to go. Otherwise, distance formula is going to take care of business really all the time, but particularly if you just have points. So looking at the first three examples, I mean, that's screaming for the distance formula. Let's recall the distance formula, and I'll write it kind of big across all three. So d for distance is equal to the square root of x2 minus x1 squared, and then y2 minus y1 squared. If your teacher wrote it in a slightly different way, but maybe it was like x1 minus x2 and y1 minus y2, that's totally fine. It actually doesn't matter what you call what. You just have to stay consistent. And so if you're using like x2 minus x1, you have to do y2 minus y1. Otherwise, the order will flip, and that causes a whole slew of weird mistakes. And so like the first thing I would do is actually go through and just declare what you're going to call x1, y1, x2, y2. Again, it doesn't matter at all. I'm going to call that x1 and that y1, which means I'm going to call this one y1. Oh, I'm sorry, x1 and y1 here. Oh, I'm sorry, 2. Oops, okay. And so that's what I was saying about staying consistent. You just have to kind of identify what's what. So moving to example 2, let's call this one x1, y1, and let's call this one x2, y2. Again, emphasizing that it doesn't matter what you call what, you just have to stay consistent with your call outs. Let's go back to doing like x1, y1, and call this one x2, y2. All right, cool. So now that we kind of know what's what, let's apply the distance formula 3 times. So let's do the first one. So distance is equal to x2 minus x1 in parentheses squared, and this is going to be y2 minus y1 in parentheses squared. All right. So in terms of what goes where, well, we need the x2 value. So x2 comes from right here. Now in this distance formula, the square root stays where it is. We're still going to have a square. We're still going to subtract. And we're going to add the two values here. Okay. So x2 minus 6 goes in its place, minus x1, okay, and x1 is right here. Now we are going to have a double negative because we have a negative from the formula and a negative from the substitution. We'll deal with that in the next step. Here we have a y2. Okay, that's going to be that guy, so it's going to be 5. And then a y1, which is going to be this guy. And again, we're going to create a double negative sign. Okay? So the thing we have to keep in mind is that if we have two negatives that are being applied in a row, that's really the same thing as just adding. Okay, so that's going to be the rule. And so if we look at this first example and how we should simplify it, okay, we have negative 6 subtract a negative 1. That's the same thing as negative 6 plus 1, or simply negative 5, and we'll square that in a second. Here we have 5 subtract a negative 6. That's the same thing as 5 plus 6, which is going to be 11, and we'll square that too. Okay. Negative 5 squared. Now you could go to your calculator, but like in the end, we have to understand a couple things. When we're squaring a number, we're just multiplying it by itself. And since a positive number times itself is positive and a negative number times itself is a positive, we're essentially just taking 5 times 5. Even though it does say negative 5, the negative doesn't matter anymore because we're going to square it. Either way, we're going to be looking at 25. 11 squared, if you go to your calculator, is 121. Or maybe you just knew it. Okay, let's go one more step of simplifying before we attack this with a calculator. We have 25 plus 121, and so that should be what, 146? And then going to your calculator, I'm using my phone, so I got to turn that sideways. I type in 146, hit the square root button, and that's going to give me, and we want to go out about 3 decimals, 12.083. And that's going to be my distance. Okay? And so the segment that has endpoints at -1, 6 and -6, 5 will have a diagonal distance of about 12.083. All right, so for number 2, we're going to experience something very similar. This should be quite repetitive at some point. Okay, so we need x2. x2 is right here. And so building in our structure, okay, x2 is going to be -2. Subtract x1, so subtract a -4. Y2 be 2. Subtract y1 is going to be 4. Okay. So in terms of simplifying, and you kind of notice I like to simplify slowly, we have -2 subtract a -4. So that's -2 plus 4, which is the same thing as 2. So we'll square that. And then we have -2 minus 4. That's going to be -2. And we'll square that as well. All right. So 2 squared is 4. -2 squared is also 4. And so this essentially is just a square root of 8. Again, that's not going to be what we call a perfect square. So go into a calculator, 8, take the square roots. This is going to be approximately 2.828. Okay, so the segment that has endpoints at -4, 4 and -2, 2 will have an approximate length of 2.828. Oops. All right, last example of this type. Again, let's go the distance. Okay, so we have x1 minus x2, y1 minus y2, also squared. If you notice, I wrote this intentionally differently than the first distance formula. I switched the x1, x2 order. And notice I also have to switch the y1, y2 order. It doesn't matter the order you write those, because we're going to be doing subtracting and then squaring. Again, you just have to stay consistent. Okay, so getting rid of my substitution step, I'll have something minus something squared, and then the y1 minus the y2 squared. So I need x1 first. x1 is going to be this 5 right here, so I'll substitute that in. I need now the x2 value. The x2 value is here, and so we have a -4. Again, creating double negatives, but we know how to handle those. Y1 is going to be 2, and then y2 is going to be -3. All right, so we have 5 subtract a -4. That's the same thing as 5 plus 4. 5 plus 4 is going to be 9, and we'll square it. We have 2 subtract -3. That's the same thing as 2 plus 3. Therefore, 2 plus 3 being 5, we'll square the next step. Okay, so 9 squared is 81. 5 squared is 25. Okay. It's getting late, so maybe I'm just going to check my calculator here. 81 plus 25 is going to be 106. And so if we take that value and then we square root it, we're going to get approximately 10.296. Right. So distance formula, quite useful in finding distances, especially if all you have are the starting and ending points. You don't even need a picture. Now, in the case that you do have a picture, though, you have some options. And so notice that we have the coordinates for P and R, the two endpoints. And so 100%, we could just use the distance formula again and call like P x1, y1 and call R x2, y2. For me personally, though, if I have a grid, I'm really all about creating these triangles. Because if we have this right triangle and we know how long the components are, namely this change in x being 3, and this change in y, 1, 2, 3, 4, being 4, I can simply use a Pythagorean theorem. Okay, a squared plus b squared equals c squared, and substitute those values in. Now, it doesn't matter what you use for a and what you use for b, as long as we acknowledge that if we're going to find this c value, we're talking about the hypotenuse, which is the exact length PR that we need. Just for like the sake of substitution, let's put 3 in for the A. Okay, let's put 4 in for the B. And that's going to equal our C value. 3 squared is of course 9. 4 squared is of course 16. That's going to be equal to C. Oh, I forgot to square. C squared. 9 plus 16 is 25. So 25 is the same thing as a squared C value. We can undo that square by square rooting, leaving the C value to be precisely 5. Which of course makes sense because in this triangle, 3 and 4 should be less than hypotenuse, which in this case is 5. And so on this last one, like, it's choose your own adventure. You like the Pythagorean theorem, we can totally use it. You prefer to use the distance formula, I think that's fine too. For me, I'm definitely going to create this triangle. Now, I think there's something wrong with this picture. Now that I look at it, it looks like it's a little bit off. Okay, so in fact, I think I'm going to change course here. Even though I could totally make these triangles, it doesn't fit on the grid line very well. I think I'm going to abort mission and just go ahead and draw, or I'm sorry, use the distance formula. So D is equal to x2 minus x1 plus y2 minus y1. I'll call this my first point. I'll call this my second point. So when I'm substituting into the equation, my x2 minus x1, x2 will turn into 5, subtract negative 3. y2 will turn into 6 minus 0. Okay, so 5 subtract negative 3, that's the same thing as 5 plus 3, that's 8. And so we'll have 8 squared. 6 minus 0 is 6, and so I'll have 6 squared. 8 squared is 64. 6 squared is 36. Okay, so 64 minus 36 would be 100, which means my distance is square root of 100, or simply just 10. Okay, so that was a weird picture, but like the distance here is going to be 10. All right. And so, like, what's the gist of this page? What do you have to know? Well, if you have a couple endpoints, and whether you have a graph or not, you can always use a distance formula. If you have a graph that's easy to count and you can kind of draw in like this nice right triangle, Pythagorean theorem is certainly in play, right? So this is Mr. Collins. Good luck. Thank you for practicing. I'll see you in the next vid.